This is Dan Schneider on this Dan Schneider video interview. The subject is extraterrestrial life. Is it rare or is it part of the mediocrity principle? I'm speaking with Jim Casting of Penn State, and the conversation will begin in a moment. Jim Casting is my guest. He is a Pennsylvania State University professor, and we will be talking about the notion of the rare earth versus the mediocrity principle in assessing the chances of life outside of this planet. Welcome, Jim. It's a big subject, and if you could just take a couple of minutes, tell the audience a little bit about yourself, what your opinions generally regarding it is, and so forth.
Okay, I'm Jim Casting. As Dan said, I'm a professor at Penn State University, split between geosciences and atmospheric sciences and meteorology. I hang around with the astronomers sometimes, though, as well. And I'm pretty familiar with the rare earth principle and book. When I was younger, I was a big fan of Carl Sagan, so my feelings lean towards the mediocrity principle rather than rare earth. But I wrote a review of the book Rare Earth by Warden Brownlee shortly after it came out, and I've got my own book, 2010 book called How to Find a Habitable Planet, that goes through many of the issues.
Well, Jim, let's talk a little bit about sort of the history of belief in extraterrestrial life over the centuries. I mean, nowadays you have the modern belief in aliens and alien abductions, and I've done a couple of shows with people regarding that. But in a more serious vein, people have thought that there was alien life that came to this planet. There's the idea of panspermia, where microbes can be floating around on asteroids or comets that hit the Earth and then seed the Earth. Regarding the historical aspects of belief in life elsewhere, is there anything notable that is worth talking about now culturally or scientifically?
Well, let's talk about panspermia. To me, that doesn't solve the problem. The real problem, or one of the real problems, is the origin of life. So if you think that life came here from elsewhere, you still have to originate life elsewhere.
Yeah.
And the related point is that panspermia within the solar system, especially within the inner solar system, for example, between Mars and Earth, is much more likely than panspermia outside the solar system, which looks to be scientifically really difficult.
One of the big ideas in talking about extraterrestrial life comes from almost 60 years ago when Frank Drake came up with his famous equation to try to estimate the chance of life. This was 20 years later on, you mentioned Carl Sagan's show Cosmos, became more publicly well known, that we would take whatever it was, 7 or 8 major factors: the number of stars in a galaxy, the number of stars that had a certain amount of metallic metallicity in them, and so on and so forth, till we could get the idea of, well, in 100 or 200, 400 billion, whatever amount of stars here in the Milky Way, what are the odds that there is another civilization out there that we could contact and have some kind of dialogue with in some manner? What is the take nowadays in astrobiology, which is what we're talking about, regarding the Drake equation? Is that seen as a relic of the past, or is that seen as something that's still useful?
I was just at a meeting last summer, about a year ago today, down at the Green Bank Radio Observatory in West Virginia, which is where the original meeting from which the Drake equation emerged. And Carl Sagan and Frank Drake were both there and co-organized the meeting. And in fact, in Carl's presence, you didn't refer to the Drake equation; he called it the Sagan-Drake equation. But the interesting thing was, at this meeting, Carl Sagan, of course, passed away a number of years ago, but Frank Drake is still alive and kicking, and he was there at the Green Bank meeting last summer. So I think the hypothesis is still out there what I would say is that, we started searching for intelligent life a long time ago because radio telescope technology has been around for a long time, and that it's actually easier in some ways to search for intelligent life than it is to search for simple life. So it's the search for simple life that I'm most interested in myself.
Well, and also too, the Drake equation sort of posits the idea that intelligent life would somehow be quote unquote humanoid. One of the things in science fiction that's always I thought kind of silly is that if you look at Star Trek or Star Wars or go back to some of the early classic science fiction authors of decades past, the idea that aliens have to be somehow humanoid to be intelligent, that they're going to have digits. Because if we're going to build radio astronomy, radio telescopes, you'd have to have digits. You'd have to probably be at least bipedal, if not more there. But I mean, if you're, what is the guarantee that intelligence, there could be intelligent, I mean, we have dolphins, for example. Dolphins couldn't build a radio telescope.
Well, no, see that, I think Sagan and Drake got that right. They defined intelligence as the ability to build radio telescopes and do radio communications. And because the reason they defined it that way is because that makes it a testable hypothesis that we could look for. Dolphins may be pretty intelligent on this Earth, but if you were looking for them on another planet, you wouldn't see any sign of that, right? So it's not that they defined intelligence as being humanoid. They defined it in a way that we can test their hypothesis. So I'm all for that.
Well, you had mentioned that you're more interested in simple life, and one of the ways that simple life could be detected is by chemical signatures from the light that comes from the native star that bounces off the planet, and we can tell that as the planet transits across the disk of whatever star we're looking at. Correct? So,
yeah.
So simple life, in a sense, I think you had mentioned, is maybe easier to detect microbes or whatnot, right?
Yeah. First of all, I should qualify that statement. Most biologists object vehemently when you talk about simple life because they will point out that even the simplest microbes on our planet today are actually highly evolved and pretty complicated. So, but by simple life, I mean not intelligent life and not necessarily even animal life, but organisms that are capable of modifying a planet's atmosphere in a way that can be detected spectroscopically.
Yeah.
And the easiest example to think of, and one that may be relevant, is that most of the oxygen in our present atmosphere was produced by photosynthesis, all of it by organisms, and so it would be if you saw oxygen in the atmosphere of an extrasolar planet, you would immediately begin to wonder whether that was produced by photosynthesis or whether there are abiotic sources.
Yeah, and for example, if you went back, 2-3 billion years ago, whatever it was, there wasn't a lot of oxygen on the Earth. There was the great, what they call oxygen catastrophe, when we had anaerobic life. So if we're even looking for life, though, we're basically talking about looking for life as we know it, so to speak, then, rather than life as it may be. I mean, there's no guarantee that terrestrial life is going to be dominant in the cosmos, is there?
Right, but I give talks on this subject, and what I often try to emphasize is that life everywhere has to have certain things in common, and that's because thermodynamics is common to every place in the universe. And even if you have organisms that are quite different from us biologically, the ways that they can modify a planet's atmosphere are actually limited just by thermodynamics and kinetic principles. So even if you had very different types of alien life, the products of metabolism on a planet like the Earth that has carbon and water on its surface are likely to be basically the same products that you see here on Earth or on the early Earth.
Well, how about something like Saturn's moon Titan? I believe it is it Titan or Triton? I forget.
Right.
Titan. Yeah, and that has methane lakes. It's got I think a thick atmosphere, the thickest outside of Earth and Venus as far as rocky worlds. And then there's Europa and I think Enceladus and maybe two or three other of the big moons around the gas giants that might have under ice ocean. Um, uh, what where do they sort of fit into our understanding of what extraterrestrial life might be like, even just here in our backyard, so to speak?
Well, I worked for NASA for a while, and I've been associated with NASA programs my whole career. NASA astrobiology, the largest part of that is focused on looking for life on exactly these types of bodies that you just mentioned. Titan and Titan, which has lakes of liquid methane, so that's very different from Earth. But Jupiter's moon Europa and Saturn's moon Enceladus both have subsurface oceans, which are probably dominantly water. So that there you might find life much more as we know it.
Mm-hmm.
And that's perfectly fine. That's what we should be doing in the solar system.
Yeah.
But there's a big difference between objects in the solar system where we can go there, or at least potentially go there, and planets around other stars where right now and for the foreseeable future we don't have the technology to go there, so we can only study them remotely with telescopes.
Mm-hmm. Let's get back. You mentioned the Rare Earth book, which was one of the jumping off points for me to want to do this show and hopefully with some other people a series of shows. And that was a book 20 years ago by Ward and Brownlee, Peter Ward, and was it Thomas Brownlee, was it?
Don Brownlee.
Don Brownlee. And they also had a very Drake-like equation, the Rare Earth equation, wherein they posited that rather than the dominant idea of the last couple of centuries, sort of this, I guess you might call it post-Copernican mediocrity of, where we're going around an average star, we're an average planet, we have, a lot of, things that aren't seemingly exceptional in the cosmos, that the Earth, in fact, is rare, that it has a large moon, that it is in the quote-unquote habitable zone around the sun, that a number of things in terms of chemical composition and whatnot in their equation, similar to the Drake equation, makes the idea that they posit that we may be the only intelligent civilization that has arisen yet in the supposed 14 billion years since the Big Bang, in this galaxy at least, if not in the rest of the cosmos. Do you see that as a bit of sort of biocentric or anthropocentric pleading on their part?
Yeah, well, there's long answers and short answers to that. I wrote a pretty long answer in my 20-page review of their book in 2001. But let me just give you a little of the history of it first. Peter Ward came, he's at University of Washington. He came here to give a public talk at Penn State in 1998, I think it was, about 2 years before the book came out. And I went to the public talk, and I distinctly remember that the thesis of his talk was that not that intelligent life was rare in the universe, but that life itself was rare in the universe.
Yeah.
And I went out to dinner with Peter with a group of people afterwards, and I sat next to him and talked about that with him for a couple of hours over dinner. And then then I had no communications with him, and when the book came out 2 years later, he changed the thesis. It was no longer that life was rare; it was that intelligence life was rare. So I think even Peter agrees that life may be a common phenomena. So he just thinks it's difficult to get up to intelligence, and that's a more interesting point. I think that's why his book, I think they sold a lot of copies, and there's lots of areas to debate in that thesis.
Well, in his equation, which has a similar amount, something like 8 or 10 factors, which do you think are the maybe one or two weakest links in that chain?
Well, let's take the presence of a large moon that you mentioned. So Earth's obliquity, the tilt of its spin axis, is stabilized by the moon today. But and that they argued, it has been shown by some very good mathematicians and astronomers that Earth's obliquity, the obliquity today is 23.5 degrees. That defines the Tropic of Cancer and Tropic of Capricorn,
Yeah.
right? And on time scales of about 41,000 years, that obliquity varies from 22 to 24.5 degrees. So there's a slight wobble of it. If you just magically remove the moon, then Earth's obliquity would vary from 0 to 50 or 60 degrees on a time scale of millions of years. The French astronomer Jacques Lescar has done some of the calculations on that. But why is that? It's for technical reasons. The rate of precession of the spin axis is commensurate with what are called secular resonances produced by the motions of the other planets. But if the early Earth was spinning faster, or if the Earth was spinning faster than a 12-hour day, more than twice as fast as it is today, then the obliquity would be regular, even in the absence of the moon, right? So then you have to figure out, well, how fast would the Earth be spinning if you didn't have a moon? The moon is slowing down the Earth's spin rate by tidal drag. So if you extrapolate back into the Precambrian, then there was a time when the Earth was spinning at a faster than 12-hour day, right? So it really depends on a whole bunch of factors, whether or not it's not obvious at all you need a large moon to have a stable obliquity.
And another thing that they talked about was the idea of Jupiter as a protector of the inner solar system. And yet, I think about a decade after the book came out, about a decade ago, there was some computer simulations which basically argued against it, that Jupiter at best was maybe neither here nor there in terms of protecting the inner solar system. And some people have said that it may have actually sent more stuff inward to the inner solar system.
Right. Well, Jupiter protects us from objects from the Oort cloud, the cloud of comets surrounding the solar system, and the Kuiper belt, which is somewhat closer in. But Jupiter sends asteroids our direction. Jupiter's at 5 astronomical units, 5 AU. The asteroid belt goes from 2 to 3.5 AU, and there's a division in the asteroid belt called the Kirkwood Gap at 2.5 AU, where there are very few asteroids. Well, why is that? That's a resonance, a mean motion resonance with Jupiter's orbit. And so when asteroids through collisions get pushed into that mean motion resonance, some of them get sent in the direction of the Earth. So like you just said, Jupiter is a double-edged sword. It prevents some collisions and causes others.
Another point, and I don't know if it's an actual formal part of the rare Earth equation, but I know that I've seen it over the years. The idea that somehow you need a fairly circular orbit. I mean, the Earth's orbit isn't perfectly circular. It's slightly, I guess, what would you call it?
Eccentric.
Eccentric. But I've also read that it could be that if the Earth had a more eccentric orbit, maybe not as eccentric as Pluto, but if it was a bit more eccentric, that might have actually helped speed up evolution, because you'd have colder winters, you'd have hotter summers, and so life, once it got started, would evolve more quickly. What is your opinion on that?
Well, this question is being solved as we speak by observations that where the astronomers are getting more and more observations of extrasolar planet systems. One thing you can say from our own solar system is that if the planetary orbits were not nearly circular, they wouldn't be stable. So you can't get 8 planets into a planetary system, 8 planets like the ones in our system without their orbits, especially the giant planets, have to be nearly circular to be stable.
Mm-hmm.
Right now, the astronomers find all sorts of examples in the planets the extrasolar planets they see. They see planets that are on highly eccentric orbits, so we know it happens. But those planetary systems are not packed with planets in the way that our solar system is. So you really the real question is how many planetary systems are stable systems with stable multi-planet systems versus how many have planets, just a few planets on more wildly eccentric orbits. The best way to solve that problem is through observation.
So, Jim, let me talk about, you mentioned the extrasolar planets, and I think I just read recently that something like approaching 4,000 extrasolar planets have been confirmed in about 2,800 star systems within, I guess, a few hundred, maybe 1,000 light years distance here in our little neck of the Milky Way. And a lot of them are very odd compared to us, which would, I think, maybe the rare earthers might argue bolsters their argument. Because we've seen, I think, some planets around white dwarfs and other smaller stars. Now, the problem there, of course, is they're not going to be as far out as our planets are. I mean, the Earth is 93 million miles on average, and most of the rest of these smaller stars that have planets, it's probably maybe 50 or 60 million as the farthest out planet that can be detected. And yet those planets are going to be tidally locked. In that they're only going to have one half of them facing it, like Mercury does our sun, and so that presents challenges on its own. In the search for these extrasolar planets, how many Earths or quote unquote super Earths have been detected, and are they actually the best planets to look for life, or could there be life on more bizarre planets?
Well, so one point I make whenever I give a talk on this is that you do need a planet with either a rocky or a liquid surface. I think it's very unlikely that life could originate on giant planets that have fully gaseous envelopes. Carl Sagan was more optimistic. He postulated life in Jupiter's atmosphere, and he actually had, in one of the episodes of Cosmos, there's a movie of these floaters look like giant air balloons going up and down in Jupiter's atmosphere. But something like that would be highly evolved. And the question is, how would you ever get to the single-celled stage of life where, a single-celled organism on Jupiter would be wafted up to the cold fringes and wafted down into the very hot interior by convection. So I would argue that, it's basically impossible to originate life on a gas giant like Jupiter. And I get very little disagreement on that. I think we all basically agree that you need a rocky planet. It could be a water world, it could have a liquid surface, but you're not going to get life on a gas giant.
So do you think that a planet, an extrasolar planet that had very little water or very little methane, as in on Titan, that could originate life? I mean, we still don't know actually how life developed here. The old thing about the murky little pond and how did cells form their exteriors, things like of that nature biochemically. It would seem to me that at least to get life started, you would need some kind of liquid that acts as a solvent for these chemicals, no?
I think we all agree on that. So the question is whether that liquid needs to be water or whether you could get away with something like liquid methane that you have on Titan. I personally am skeptical of life on Titan because you're at a surface temperature of, 90 Kelvin, I think, and chemical reactions are very slow. The activation energies are hard to overcome. So I personally think that you have to have something more like liquid water that's liquid at at a higher temperature. And the fact that water is a polar solvent with, its charge separation between the oxygen atom and the hydrogen atoms, that may well be important too. Whereas liquid methane is nonpolar, and they dissolve entirely different types of things.
Well, sticking with the sort of chemical approach, I was just recently reading this morning, in fact, just in preparing for this, about some people hypothesizing that life may not have to breathe oxygen, that hydrogen, there could be forms of life that respire with hydrogen. Is that something that is taken seriously in astrobiology?
Well, I wouldn't call it respire, because respire means, technically it means using oxygen to produce energy. Now you can expand that to sulfate. Some people talk about respiration with sulfate, but using sulfate as the source of the oxidant. Hydrogen is there are organisms that use hydrogen for photosynthesis. So you can, take hydrogen plus water and make organic matter, plus CO2 and make organic matter out of that. And so that's perfectly fine. You don't have to have oxygen, free oxygen in the atmosphere to have life.
Mm-hmm. Well, how about on like Europa? Because if the life is underneath the ice and not within the ice, wouldn't that need something like chemosynthesis rather than photosynthesis to get going? And would a world like that, do you think that there would be kingdoms like animals? I think it's kingdoms: animals, plants, archaea, bacteria. Or do you think that it would just basically be maybe just floating giant algae under there?
I think it's more likely to be bacteria or archaea, anaerobic organisms that don't require oxygen, because it's very unlikely, I think, that you have much oxygen in Europa's subsurface ocean.
Yeah.
Oxidants are very limited down there. There may be a lot of reductants from, if there are hydrothermal vents at the bottom of the ocean, which there may well be, then the fluids coming out of those are probably quite reduced.
And even something like that, I mean, from what I've read, do most people think that Europa has even a rocky core, or is it basically just a giant snowball with liquid in the center?
I think it has to have a rocky core, although I'm not the world's expert on Europa.
So let me talk about one of the staples of science fiction about other life as we don't know it, silicon rather than a carbon-based life. Is that plausible, or is this just the stuff of sort of 1950s sci-fi?
Well, I grew up in the 1950s reading sci-fi, so I'm quite familiar with the concept of silicon-based life. I also talk about that. Silicon's right below carbon in the periodic table of elements, and so that's why it's been suggested. But its chemical behavior is quite different. So both silicon and carbon bond with oxygen, but silicon bonds really strongly with oxygen to make things we call rocks. And then once you form those SiO bonds, they're very difficult to break. Whereas carbon bonds more weakly, forms carbon monoxide and carbon dioxide, and you can break those bonds, especially the CO2 bond, by using photons from the sun, right, or using chemical sources of energy. So I actually, even though I like science fiction a lot, I don't think that there's silicon-based life anywhere.
Mm-hmm.
That doesn't really do the same type of chemistry that carbon is capable of.
One of the things that in terms of astrobiology people talk about is not only there being a habitable zone around stars, but a quote-unquote galactic habitable zone, meaning that star systems that might be too close to the galactic core, where most galaxies are thought to have huge black holes that emit all sorts of deadly radiation, that you'd have to be sort of in the, what I guess you call the galactic suburbs, the outer rings, as our solar system appears to be, to be able to form at least life that isn't going to be snuffed out after 1,000,000 years or so. Um, uh, how likely do you think it is that life could exist in the inner core, the urban, the inner urban area of a galaxy?
Well, you know, Charlie Lineweaver from Australian National University has written probably the best paper on the galactic habitable zone, and there's certainly some validity to that argument. But the galactic habitable zone is pretty wide to begin with. It includes much of the galaxy, according to Charlie. And the other thing that is sort of mitigates against that is that stars move around quite a bit in the galaxy. They don't just move in circular orbits, staying at their same distance from the center. So, you know, stars could meander in and out of the galactic habitable zone, and, you know, carrying their planetary systems with them. The other thing I would say is the galactic habitable zone is actually so big that in the next few centuries, we're not going to be able to explore more than a tiny little chunk of that in our own solar neighborhood. So for the present time, it's almost an untestable concept.
Mm. I want to get back to the idea of life as we know it, and I want to talk about two of the most famous sort of non-humanoid ideas about aliens. One is Stanislav Lem's Solaris Ocean, the idea that there could be a linked chain of being that, let's say, if Europa maybe had something similar to that, or and then the other one being Fred Hoyle's famous black cloud, meaning that you could have these giant clouds, maybe the size of a solar system, just protein, organic matter floating around, that after hundreds of millions of years, somehow they form primitive, maybe, or maybe even not that primitive, kind of networks of communication within, and it takes on the form of, say, we have, for example, super organisms. People can look at an ant colony as if it was a single animal rather than made of constituent insects. What is your take on those more speculative kinds of life forms, the life form that's like a Solaris Ocean or Hoyle's black cloud?
Well, first of all, I read both of those books. I told you I read a lot of science fiction growing up, so those were on my on my reading list. You know, they're fun ideas, and they're great science fiction books. But I personally think that you're not going to find that. I think life, you know, take the black cloud idea that it, you know, an interstellar cloud could be alive. I think life has to start small, and it has to start at the cellular level. So, of course, you know, we debate at original life meetings what it takes to form life. But my feeling from having gone to many original life meetings is that life elsewhere will be like us in many ways. It will form on a planetary surface, not out in space. It will start small. And so the question for Solaris is, how do you get from small to something where the whole ocean of the planet is sentient? So I don't know. I consider those more science fiction than science. And you know, I'm mostly interested in testable hypotheses. So if you can figure out ways to test those hypotheses, that's great. But other than that, they're sort of like angels on the head. How many angels can you fit on the head of a pin, which used to occupy theoreticians back in the Middle Ages?
Yeah. And how about the idea of life as we don't know it? When we talk about, even here on the Earth, there's been an ongoing debate for, I guess, since viruses were discovered, whether or not they are actually alive or they're just sort of miscreant pieces of semi-life or partial life. Do you believe that viruses are living things yourself?
Well, what I believe is that the distinction between living organisms and between life and non-life is not as sharp as you would like to believe. Viruses are somewhere in between. And that's fully consistent with the theory, the theory of the natural origin of life, that life arises somehow spontaneously from non-life, right? So it's a continuum. It's not completely distinct.
Well, I mean, isn't one of the things that we define life is motility, the ability to move around, the ability to process uh, energy in the form of food of some sort? And do viruses even do that?
Well, viruses can't reproduce themselves,
Yeah.
so by that definition, they're not alive. But if you get them inside an organism that is alive, they can reproduce themselves very rapidly, right? Look at COVID-19, that's doing that in lots of people around the world these days. So I think, viruses by themselves can't exist, but as soon as you have life, as soon as you have organisms that can exist, viruses probably came along immediately thereafter, because they're pieces of chemistry that can take advantage of that and use that to replicate themselves.
I want to sort of throw a few things at you. One of the things that I've often had debates with some scientists and also mathematicians is universal constants. It would seem to me that if we're looking for life elsewhere, we have to make the assumption that there are constants in the universe. A lot of people talk about a finely tuned universe. In other discussions, I've talked about whether mathematics is a natural part of the cosmos, or is math simply a language, how we talk about things. So I would assume that astrobiology works upon the assumption that here in the Andromeda galaxy, or in galaxies a billion light years away, that things are pretty much the same in terms of universal constants. What's your take, first off, on what are called fine-tuning? Personally, I think that's very anthropocentric or biocentric, the idea that there's a finely tuned universe, because then there'd have to be a tuner, would there not be?
Right. So that invokes a creator, which some people believe in and others don't. One common theory that I've seen, I think Paul Davies may have written about this, is the idea that there's a multitude of universes, and that we happen to be in one that is finely tuned, but that there's, I forget what his term for it is, multiverses or something. It's fun. Paul is a bright guy. He likes to speculate, but again, I'm mostly interested in testable hypotheses, and I don't think that's testable as far as I know. The question of whether the universal constants are the same, like the fine structure constant and whatnot, they probably are within our galaxy. The more important question is, do they remain the same over time? There's a principle, if I remember from my undergraduate physics, I think it's called Mach's principle, that suggests that the different constants of nature may be related to the structure and size of the galaxy, so they may change with time. Mach's principle. Anyway, if you can test that, that's great. I'm not a good enough physicist to have an informed opinion on that. Everything we can test says the constants are the same everywhere we can test them.
So let me just sort of also throw this out. We have here on the Earth, we have evolution, the survival of the fittest, the idea of that competition, and the idea of cooperation between life forms. It does exist, but it's very minor. Is there an assumption between astrobiologists that evolution, because certainly creatures would have to evolve elsewhere if they're going to get intelligence, that competition is likely to be the norm, or that can we imagine worlds or scenarios for planets where those species that survive and do better are those that actually form cooperative bonds. In other words, is competition, red in tooth and claw, likely to be the norm or not, do you think?
Well, that's a question for an evolutionary biologist,
Okay.
which I'm definitely not. But there are examples of cooperation, lots of them on Earth. The term is called symbiosis, organisms that depend on each other. And the only one that I can remember off the top of my head is corals, which are symbiosis between, what is that? It's an algae and a cyanobacterium, I think, for corals. Now, in general, there's a lot of competition in nature, and so that I expect that would be the norm, but that doesn't preclude cooperation. And these days, now that we have the capability, we try to do a lot to protect other mammal species that are in danger of extinction, right? Lions and tigers and pandas and all sorts of creatures that we would like to keep around on the Earth. So that's a form of cooperation.
Mhm. Another thing I wanted to ask you about is in the idea and the study of certainly intelligent life, there's what's known as Fermi's paradox, which I've often thought was really, I find to be a silly thing, because I don't think it's a paradox. In order to have a paradox, you have to have empirical proof of something that is contradictory. And since we don't have any proof, we've only got one planet that we know of in the universe that definitely has life and definitely has intelligent life. The idea of Fermi's paradox, which is that life should be plentiful, why haven't they come here? To me seems it's not a paradox. I mean, first of all, putting aside their need to get life and get intelligent life, why would they want to come here anyway? I mean, we're smaller than a microbe on the cosmic scale. The idea that alien life would come to visit us and say hello and take me to your leader, that kind of thing, seems a reductio ad absurdum.
Well, I have read some of the literature on Fermi's paradox, and from what I've read, actually, Fermi didn't suggest it as a paradox himself. It was brought up at a lunch conversation that he was present at, and other people pushed the idea. Fermi himself didn't believe that interstellar space travel was possible. Yeah. So it's basically what you said. If you can't travel interstellar distances, then it's not really a paradox that we haven't seen aliens here. But if you postulate that interstellar travel will become possible at some point, then it becomes, it might be a paradox. Mm-hmm. And there's a different classes of solutions to it. The one that I'm fond of is called the Great Filter. Have you heard of that one?
Yeah. That there's some event that prevents, whether it's a global catastrophe caused by the intelligent species or.
Yeah. So that this gets back to the rare earth question that you started out with. The Great Filter is some really difficult step in evolution between the origin of life and the development of a civilization capable of interstellar travel. And so, the book Rare Earth, the Rare Earth principle postulates that the Great Filter is behind us. It's very difficult to get, as I said earlier, Ward and Brownlee believed that life itself may be common, but that intelligent life is not. So that would imply that the Great Filter is somewhere between simple life and intelligent life. My personal feeling is that there is a Great Filter, but that it may be ahead of us rather than behind us. And, the filter may be that intelligent civilizations destroy themselves or damage their planets before they ever have a chance to develop the capability of interstellar travel.
And that also posits the idea that intelligent life elsewhere would have the same cultural predilections that we do. I mean, what is to say that if I grow up and I'm part of life on some alien world, quite different from Earth. Why would there be a need if we are getting all the energy we can from our local star, if we have a flourishing culture that satisfies our needs? Maybe they're not moved to go explore the universe. It seems like we're trying to impose the idea that that intelligent life must explore the cosmos.
Right. Okay. So that I'll give you that. That may be the problem, but I would say if there is intelligent life elsewhere, it will have some things in common with us. For instance, the aliens will very likely breathe oxygen as we do, and that's for good biological reasons. There's so much energy available from respiration compared to other forms of metabolism that I don't think you can get to organisms as complex as animals and intelligent animals without O2 around. Mm-hmm. The other thing that I'll say, which is maybe more relevant to the Great Filter, is if you have intelligent civilizations that develop technology, they're going to go through a fossil fuel burning stage, just exactly like we're doing right now. And so they'll have the capability of altering their planet's climate in a major way. So that is something that I worry about. That we usually refer to that as global warming. We could actually do a lot of damage to the habitability of this planet over the next 50 to 200 years if we don't recognize that and start reducing our dependence on fossil fuels.
So, as I sort of wrap this up here, it seems to me that you, even though you disagree with Ward and Brownlee's ultimate opinion, you seem to accept some of their posits, i.e., that you, from what I'm getting, you tend to think that life is abundant, but that intelligence may be rare, and that it would have to be oxygen-based life. It would have to be probably carbon-based life, and it would probably have to be, if not tetrapodal, it would have to have some kind of digits to manipulate the world about it. You can't get from one planet to another by having nice flippers or whatnot.
And you can't build radio telescopes without some kind of fingers.
Yeah. So so it seems to me then that you do accept probably a good deal of the things that Ward claims, at least as far as the creation of the aliens themselves, if not on a planetary level. Is that correct? So what is then the main, if you, the one or two things where you think the rare Earth hypothesis maybe is gilding the lily too much?
Yeah, well, see, the rare Earth hypothesis, another way of saying that is that the Great Filter is behind us. That it's a very difficult to get to the stage that we're at today, and then they go through a whole list of reasons, including the moon thing, but there's about 9 or 10 other ones. And where I disagree with them is I think the Great Filter, if there is one, is ahead of us, not behind us. So I think that if life arises on other planets, which I think it probably does, then the chances that it will eventually get to intelligent life are pretty good. Mm-hmm. And we could spend a couple hours talking about the detailed points in Ward and Brownlee's argument, but I don't think there's necessarily any showstoppers there in getting up to humans.
Yeah, earlier this morning when I was looking online, I saw just 3 or 4 weeks ago there was a release by some group that claimed that there's likely to be 36. They used 36 civilizations at any given time in the Milky Way at our level or above. And I just was sort of astounded as how they could be so precise with their number. But what if you were to take a guess, your own intuitive idea? Let's say between 100 and 400 billion stars. Let's split the difference. Say there's 200 billion stars in the Milky Way galaxy. How many worlds do you think would have? And when I say world, I don't mean just planets. It could be moons around giant Jupiter-like planets too. How many instances of life do you think there are, percentage-wise, from that 200? Do you think there's maybe, 1 billion worlds that can have life, and of that, how many do you think would be at our level or greater, intelligence-wise?
Well, my guess, we know some of the factors in the Drake equation a little bit now. One of the ones we didn't know when that equation was constructed was the fraction of stars that have rocky planets within their habitable zone. So now from the Kepler Space Telescope and from ground-based radio velocity measurements, we have some estimates for that. We know that at least 10 or 20% of M-stars have planets in their habitable zone. And we don't know the numbers as well for sun-like stars, but there's no reason to think that it's less than 10%. And my personal guess is that if you have a sun-like star with a planet that with a 10% chance of having a rocky planet in its habitable zone, most of those will develop life, because I think life is a common phenomenon, not a rare one. And some fraction of those will evolve to intelligent life. But then to the question of how many intelligent civilizations exist at one time, if you've studied the Drake equation, most of the uncertainty lies in the last factor, which is the lifetime of a technical civilization.
Yeah.
And so you get back to the great filter argument that I just gave. If technical civilizations destroy themselves within a few hundred years, then the number of existing technical civilizations is going to be very small.
Yeah.
Right.
And I mean, if you just went back 500,000 years here, you'd have had basically the same amount of time and not a single technological civilization. So again, you could have a flourishing world, but it's basically going to be an Eden.
Yeah. So we can speculate till we're blue in the face. To answer any of these questions, we need observations, and those can be done with either radio telescopes or lasers for looking for intelligent life. For simple life, we need some big space telescopes that we call direct imaging telescopes that can look for Earth-like planets around nearby stars, not just ones that transit their star. And so that's what I'm hoping to see get launched within my lifetime.
And in your lifetime, let's just the final two questions I would ask then. What do you see, say, in the next couple of decades? Let's just go to the middle of the century here. In discoveries awaiting us for the planets, knowledge about planets, an increased knowledge about extrasolar planets, and also do you think that by 2050 we will have gotten that signature from this, that, and the other world that, there's a 98% chance that there are aerobic creatures there?
Well, a lot of that depends on what the astronomy and astrophysics community decides. Right now, they're going through this exercise of planning doing their next decadal survey. And there's two big space-based telescopes, one called HabEx, the Habitable Planets Explorer, and one called LUVOIR, the Large UV Optical Infrared Space Telescope, both of which would be capable of looking for Earth-sized planets around all the nearby stars and taking spectra of their atmospheres. So if one of those gets picked, then they could be built and launched by about 2035, and we might have the answers within 5 or 6 years after that. Mm-hmm. If they don't get picked, there's a good chance they won't get picked because NASA's having so much trouble with the James Webb Space Telescope. So if they don't pick those, then it'll delay the direct imaging for another decade after that. So it won't be till close to 2050 until we can get any answers.
And do you think that the discovery of life elsewhere, even if it's just microbial life, whether it's here in the solar system, but especially outside the solar system, where it's likely to be more pristine, there's not going to be any chance of panspermia between nearby worlds in a solar system, do you think that's going to have any real effect on society? Or do you think in our own society, people are going to be, oh, yeah, but I've got to still watch the Kardashians?
Well, I think it would be just revolutionary. In fact, my colleague at MIT, Sarah Seeger, is more eloquent than me when she gives a talk on this. She describes that as it would be the second Copernican revolution. In the first Copernican revolution, we figured out that the Earth goes around the sun, and not vice versa. And you can argue that that doesn't affect our lives, but it does. It affects our whole outlook on the universe. And I think equally so, or maybe even more so, if we discover that we're not the only living organisms in the entire universe, it will change our philosophical perspective, hopefully in a good way.
And finally, Stephen Hawking, before he died, and a number of other people have, they sort of sounded the alarms about, let's not advertise our existence because, there could be the Borg or the Galactic Empire out there willing to just crush us or whatnot. But it seems to me the more likely thing is, let's say if we found a world very similar to Earth within, I don't know, 20, 30 light years, that conceivably within a few hundred years we'd have the technology to get there in a few decades, or maybe even by going faster than light. It would seem to me that I wouldn't want human beings coming to my planet, especially if there's a gold rush there, especially if we find minerals or things that we can use. It would seem to me that we've done such a lousy job on our home world that we would, by us going to another world, we might just totally destroy. I mean, we're talking genocide upon genocide. I mean, planetary, do you sometimes worry, do people in astrobiology, are there protocols that, let's just say nearby, let's say in the next 100 years, we did find life on Europa. There was the 2001, 2010 book, Do Not Touch Europa, from the gods that made the monolith. Are there protocols that we have in place that we don't fuck up other worlds, basically?
There's planetary protection within the solar system. We don't have any protocols on planets outside the system. There is controversy on this. I'm sure you've heard of SETI, the Search for Extraterrestrial Intelligence. There's a group called METI, which is Messaging Extraterrestrial Intelligence. And their goal is to send out signals to nearby stars and tell anybody that's there that we're in existence. I went to one of their meetings a couple of years ago just to see what was going on. That's controversial because there are people, as you say, who are worried about that.
Yeah.
I'm not that worried about it. I think if there are any civilizations, any intelligent beings within our area of the galaxy, they're either going to be way far ahead of us or way far behind us in development.
Yeah.
We're 200 years past the dawn of the industrial age here, and 100 years, less than 100 years after the invention of radio telescopes. So which is a tiny chunk not only of human history but even smaller of Earth's evolutionary history, right? So the chances of finding another civilization that's right where we are that would have the same goals and desires is just minuscule.
Yeah.
Right.
I remember, speaking of science fiction, there's a famous science fiction story. I can't remember who did it, but some alien intelligences are looking at Earth, and it ends up with the revelation that one of the aliens says to the other, but they're made of meat, or something. And it would seem to me, like you said, that if you're capable of interstellar travel, not in, who knows, even if intergalactic travel is capable. I mean, they're so far beyond us. It's like us worrying about, ants. I mean, yes, ants can be dangerous. If a killer ants or whatnot, carpenter ants or whatever they are, come and swarm you. But overall, an ant isn't going to affect something. So anyway. I will link to your page at Penn State University. It was a good conversation. And anyone who wants to contact you there, who enjoyed this conversation, can contact you there. So, Jim Casting, thank you for spending about an hour talking about extraterrestrial and intelligent life.
Okay, it's been fun.